Hello students, my name is Vidisha Mujumdar and today again I have come with you to share the second part of our previously left chapter, which one is the solution of class 12. In the previous chapter, what we have learned? We have learned about the introductory part of solution chapter, which is what is solution, how many types of solutions are there, what are the concentration, how to make the concentration of the solution, about normality, molarity, formality, and some numerical sums I have discussed, and what is the difference between the molar solution and the molal solution. And now I have come with the second part of this solution chapter. I hope all of you have gone through the topics which I have covered in the previous chapter, previous day, and now I am going to take the topic which is known as the mole fraction. We know that what is called mole fraction. What is called mole fraction? Fraction, here a term comes, that is the ratio. So the mole fraction is the ratio of the number of moles. Ratio of the number of moles of a component to the total number of the moles of all the component present in the solution. So it is the ratio of the number of moles, total moles of the component, moles of the component divided by the moles of the total mole of the component in the solution. So that is called as mole fraction. So how can you denote this mole fraction? Mole fraction of the component can be derived in mathematical representation. It can be said as number of the moles of that component by total number of the moles of all the components present over there. So number of moles of that component to the total component present over there. Suppose for a binary solution, if the number of moles of a solvent and the solute are N1 and N2 respectively. Binary solution means there are two solutions, and in binary solution, suppose the number of moles of solvent and solute, that is denoted by small n1 and n2 respectively. Then the mole fraction of the solvent x1, so the mole fraction is denoted by x1 is equal to n1. This is the number of the moles in the moles of the component divided by the total moles of the component, that is n1 and n2. So this is for the solvent x1, and for the solvent mole fraction for the solute x2. So the solute is taken as x2. So the solute is taken as x2, and the mole fraction of the solute which is represented by x2 can be denoted as n2 divided by n1 plus n2. So again we can say that n1 is the this is the moles of the solvent and solute. Moles of the solvent. This one is the solvent, this one is the solute. So I can write this as number 1 and number 2. So now the mole fraction, I hope all of you have written. So the mole fraction of the solution will be mole fraction of the solution will be what I have written, that one, number 1 plus number 2. What was number 1? As there is lack of space, so I have to recapitulate what was the number 1. Number 1 was n1 by n1 plus n2, and what was number 2? n2 by n1 plus n2. If we add these things, the term adding is there, if we add these things, then what will happen? n1 plus n2, this will be the LCM. So here it will be n1 plus n2. So these two terms are getting cancelled. So getting cancelled, it will be 1. So the mole fraction of a component is a unit fraction. So the mole fraction of the component is becoming unit. So the mole fraction of the solvent. So up to this, it's clear, I think. So the mole fraction of the solvent, mole fraction of the solvent is equal to what was there? solvent x1 is equal to 1 minus x2, and mole fraction of the solute x2, it will be 1 minus x1. So the mole fraction of the solvent, that was, what was the solvent? It was x1, it will be 1 minus x2, and the mole fraction of the solute x2, it will be 1 minus x1. So it has no units. Why it is not having any unit? Because this is a ratio of two terms, number of moles in that component divided by the total number of moles. As this is a fraction, this is a ratio, so it is not having any unit. So unit is not there. So this mole fraction is independent on temperature. Is it dependent on temperature? No, this is not dependent on temperature. So this mole fraction is independent on temperature. Why it is independent on temperature? Because here the term moles is coming. So this mole, this is the intrinsic property of the particle. This is having, this is not depending on the temperature. So the whole term is not depending on temperature. So this up to clear? The term mole fraction, this is a very important term along with the other terms which were normality, molarity, formality, percentage concentration, and this mole fraction. Now I am coming to another thing. Suppose I am taking some water in a beaker. And I am adding some salt. This is the salt I am adding to it. A pinch of the salt in it. And let us stir it. Then what will happen? After some time, if we stir it continuously, what will happen? The salt will dissolve throughout the liquid, throughout the water, forming a uniform solution. And this is neither but homogeneous solution. We have talked about homogeneous solution, and if you make this type of solution, this is the homogeneous solution or true solution. Here no interface is there. The total that it is a uniform solution or uniform mixture. Now why this salt is entering into the solution? Why this is entering? Perhaps all of you have gone in class 9. There was a chapter was there, matter in the surroundings. You know that liquid are having some spaces between them. The space between one particle of a liquid and another particle of a liquid is very much more, and the force of attraction between them is very less. So there are lots of interparticle spaces, that is called interparticle. So there are lots of interparticle spaces in the molecules of the liquid or water. So this salt is entering into that particle, giving rise to a homogeneous mixture. Now another thing, all of you have experienced this thing. If we take potassium permanganate, I have not gone to school, so I was not able to take potassium permanganate from the school, so I have taken here blue. Suppose resume that this is potassium permanganate. The potassium permanganate, the color of potassium permanganate is violet in color. All of you have learned in the previous chapters and classes. The potassium permanganate is violet in color, and if you add a pinch of drop into the water, then the whole water will turn violet in color. Suppose take it is that potassium permanganate, but the color is blue, so the whole water will be violet in color. Why that color is imparted? This color is due to the MnO4. This is due to the MnO4. What is there in potassium permanganate? This is the symbol. So KMnO4. that particles, that color is imparted by the MnO4. These splits into the solution, giving rise to the color. Okay, so I will continue with another topic. This was skipped, so I have mentioned this one. Solubility of the gas in the solubility. This is another one, another important topic. Solubility of gas in liquid. Solubility of the gas in liquid. We know that there are lots of gases which are dissolving in water. For example, in the aerated drinks, all of you are taking this aerated drinks in the summer season. These in the aerated drinks, which I mentioned in the previous class also, what happens? The carbon dioxide is compressed, is bound to enter into water under high pressure. Without application of the pressure, it will not mix with the water. So this is not a general term. That's why we are forcing this carbon dioxide to enter into water, to mix into water. What happens when we remove the lid or remove the cord? Then some bubbles are coming out. From where the bubbles are coming? These are not coming from the solution. These are coming from the excess or the dissolved carbon dioxide which is added to the solution. So carbon dioxide is dissolved in water, can be dissolved in water. Can you name some of the examples of the gases which are found in the liquid form? Some example you easily see in the home. Suppose LPG. What is the full form of LPG? Liquid petroleum gas. All of you know. This is a very in general term, like liquid petroleum gas. This LPG, this is a gaseous form. This is the gaseous form of this is the gaseous form. These LPG under high atmospheric pressure, under high pressure and low temperature, this is liquefied. This is liquefied, and in the cylinders what is given? This liquid petroleum gas is given, which is coming out through the nozzle of the gas stove. When it is coming out, then it is coming out in the vapor form. As this is compressed, highly compressed to form the liquid structure, but this is not in generally the liquid form. Then you have seen in the hospitals. What happens in the hospitals? Oxygen cylinders are given. Why these oxygen cylinders are given? And is oxygen in liquid form or gaseous form? Obviously oxygen we are breathing, we are taking oxygen. This is in the gaseous form. But if we compress the oxygen, if we exert high pressure on oxygen at low temperature, then this oxygen becomes liquid. This liquid is then inserted into the oxygen cylinders to provide to the patients. So these two gases, these two gases, and these three gases are generally found in the gaseous form, but they are liquefied to form liquid. They are generally liquid. Under what are the conditions? The conditions are high pressure and low temperature. High pressure and low temperature. So have you noticed that how do the animals and plants under the sea surface, they are living in the ocean bed? There are lots of species of animals and plants. Zooplanktons are there. You have gone through in the biology chapter. Zooplanktons are there, phytoplanktons are there. How they are surviving? We know that how they are surviving. This is because of the dissolved oxygen. Oxygen gas is dissolved in water, in the ocean bed, in the water. This oxygen gas, carbon dioxide gas, is dissolved in water. As because these gases are dissolved in water, so the living organisms, the zooplanktons, phytoplanktons, they can take that dissolved oxygen to meet up their needs. So the solubility of the gas in liquid. What was our topic? Solubility of the gas in our liquid. It is defined as the maximum amount of solute that can be dissolved in water. Maximum amount of solute dissolved in water. I have taken just a few minutes ago, I have taken some salt and I have made a mixture. Here I have taken a very small pinch of the salt, but if I add maximum amount of the salt, then the maximum amount of the solute which is dissolved in water, up to which after exceeding that part we cannot dissolve more solute into the water, that term will be called as solubility. So the solubility of a gas in a liquid is the maximum amount of the solute that can be dissolved in a given solvent, which is generally water. Solvent can be water. Water is a universal solvent, so generally water is taken. So this solubility term, it is depending on some factors. What are the factors? What are the factors? The factors are, it depends on the nature of the solvent, solute. It depends on the temperature. It depends on pressure. These are the most important things on which the solubility of a gas is depends on the nature of the solvent. So what will be the nature? What will be the nature? That on that term this solubility is depending, and obviously on temperature it will depend. If the temperature is increased, then it will be more soluble. Suppose if I heat this solution and go on stirring and stirring, then more amount of salt can be dissolved in the water. So if the temperature is increased, then the solubility of the solute will also be increased, and if the pressure, it is also dependent on the pressure. So we can see that, suppose here I have drawn a picture, though I am not very good in drawing. All of you are very good in drawing, I know. So suppose here water is taken, and here suppose a beaker is taken, and here water is taken, and here the pressure which is present in the atmosphere, this is exerting one pressure on the liquid, and this surface this is experiencing the maximum pressure of the gas on the liquid. So the solubility will increase if the force of attraction between the gas surface and the liquid or the solvent is more. If the force of attraction is more, if there is more chemical reaction, then it will be more soluble in the solution. Here initially what happens, suppose a gas is dissolved, oxygen gas I have dissolved in water to make oxygen cylinder, then initially the rate of dissolution is greater than the rate initially when O2 is added to the water. So initially the rate of dissolution is very high, that in that stage oxygen is very active and it is very dissolving. So in that stage it is very active, and it is the rate of dissolution of the gas is very high compared to the rate at which the gas is leaving the state. As a result, the concentration of the dissolved gas in the liquid increases. So in the first time what happens, the rate is very maximum. As a result, the concentration of the oxygen dissolved in water is increasing. So up to this it is cleared. Then coming to another topic, which is called solubility coefficient. So now I am going to discuss two topics, which one is solubility coefficient and another one is absorption coefficient. What do you mean by solubility coefficient? It is defined as the volume of the gas dissolved in unit volume of a liquid to form a saturated solution at an experimental temperature and 1 atmosphere pressure, defined as the volume of the gas. What is meant by volume of the gas? It is defined as the volume of the gas dissolved in 1 unit. Suppose 1 unit means, in unit means 1. So if I take 1 molecule of the gas in 1 liter of the solution to form a saturated solution. What do you mean saturated solution? Saturated solution is that solution which cannot contain excess amount of the solute dissolved in it. That is, it is saturated, totally filled. No addition of solute can take place. No addition can be taking place. So it is solubility of a coefficient is defined as the volume of the gas in unit volume of a liquid. Volume of the gas dissolved in one amount or one suppose 1 molecule of the gas is dissolved in 1 liter of the solution to form a saturated solution. Then it is at experimental temperature and 1 atmosphere pressure. 1 atmosphere pressure or 1 atm pressure. Then it is called as solubility coefficient. So then coming to the next one, absorption coefficient. What do you mean by absorption coefficient? It is defined as the volume of the gas reduced to STP dissolved by unit volume of a liquid at the temperature of the experiment under a partial pressure of the gas of 1 atmosphere. It is defined as the volume of the gas reduced to STP. Volume of the gas is reduced to STP dissolved by 1 unit volume of the liquid at that temperature. If 1 unit volume of liquid is added to that solvent, then the volume of the gas is reduced. Then the volume of the gas is reduced at the temperature of the experiment under a partial pressure of the gas at 1 atmosphere. And the partial pressure of the gas is 1 atmosphere. So what does it mean? That the volume of the gas is reduced to 1 unit volume of a liquid at the temperature of experimental under the pressure of the gas, under the partial pressure of the gas of 1 atmosphere. So here in this case reduction is there. So what we have learned today, we have learned about the solubility coefficient and about the absorption coefficient. So now we will discuss about the nature of the gas and the liquid which form the solution. The solubility of a gas in a liquid increases with the increase in the intermolecular force of attraction that is seen between the molecules of the gas and the liquid. Gases like H2, N2, O2, helium are possessing weak intermolecular force of attraction. So whether a gas is dissolving in water or not, that is depending on the intermolecular force of attraction. If there is a strong intermolecular force of attraction between the gas and the solvent, then it will dissolve very rapidly in the solution. But if there is a very less intermolecular force of attraction, then they will not readily dissolve in the water. So suppose, and which are the gases which are not dissolving in water? These are hydrogen, nitrogen, oxygen and helium. They are not generally they are not dissolved in water. They are dissolved in water by applying high pressure, and at high pressure and at low temperature these gases are forcefully bound to dissolve in the gases. Why these are not dissolving in water or any solvent readily? Because there is a weak intermolecular force of attraction in these gases. In hydrogen, in nitrogen, oxygen and helium, when oxygen is dissolved in water or any solvent, then the force of attraction between the oxygen molecule and the water or the solvent is very less. They are not attracting. The attraction is very less. As a result, they are not dissolving in the solution. So these substances, these gases, they are not readily dissolved in the solution. So and easily liquefiable gases. Which are the gases? They are easily liquefiable. They are carbon dioxide and sulfur dioxide. Carbon dioxide, I have given this example many times. This is aerated drinks. This carbon dioxide is easily dissolved in the aerated drinks, for which they are easily liquefiable. These gases are very easily liquefiable, so they can dissolve in water, any solvent, very readily. So this carbon dioxide and sulfur dioxide, what happens when they dissolve in the water? They are not needed, very less pressure is very more pressure, high pressure is not needed to dissolve them. There is a strong force of attraction between the molecules of carbon dioxide and the molecules of that particular solvent in which they are dissolving. There is a very strong force of attraction. They are easily liquefiable for that reason only, as there is a strong intermolecular force of attraction. What do you mean by intermolecule? Intermolecule means within the two molecules. There is a force of attraction between the two molecules of carbon dioxide and also the molecules of carbon dioxide and that particular solvent in which it is dissolving. And the next one is the ionization of the dissolved gas in a liquid. We know that there are lots of ionic solvents. These are ionic solvents which are readily dissolved in water, which can ionize easily. For example, HCl, hydrochloric acid, these are easily ionized. When HCl is dissolved in water, what happens? It forms H plus and Cl minus. So this is highly dissolved in water. Hydrochloric acid is highly dissolved in water. So for this reason, the ionization of a dissolved gas in a liquid increases the solubility of the gas. So the more the gas is dissolved in water, the more the ionization of the gas takes place, the more readily the gas ionizes, breaks up into positive and negative ions, cations and anions. The more is the dissolution of the gas. So HCl, when dissolved in any solvent, suppose in water, then they easily reacts with water. They easily dissolves in water and they are easily liquefiable. So these are the points in which the nature of the gas and the liquid, these are the points in which the gas is dissolving in a liquid. So what I have said previously, these are the gases which are not readily dissolved due to one, intermolecular force of attraction. What was the intermolecular force of attraction? The intermolecular force of attraction in these gases is very low, and the intermolecular force of attraction in carbon dioxide or sulfur dioxide is very strong. For this reason, these are easily dissolved in water, and the ionization or liquefaction capability, the more the solvent or